Hi, everyone. This is Dr. Nigro with a Chem Calculation screencast. This screencast is going to focus on part of our kinetics unit, which is going to deal with differential rate laws. Now, I discussed in an earlier screencast relative rate laws, where you look at how the concentration of products and reactants are changing over time within a chemical reaction. Differential rate laws is going to be different. All right. So a differential rate law expresses the rate of your reaction as proportional. I always spell that wrong. Proportional to the concentration of the reactants raised to a power. So it's going to look really different. There's not going to be a delta change in concentration over delta time. All right. The other piece that's really different is this is reactants only in these rate laws. It does not concern itself in any way with the formation of the products. It's only what's happening to the reactants. All right. Now, couple pieces of information. The power that's mentioned. All right, that must be determined experimentally. And I've got some examples of how to do that. And that experimental data is going to be from what's called initial rate data. All right. And so you might ask, well, what is initial rate data? All right. So if you see, I've got a plot here of the increase in volume of a gas. All right. Now, I realize this is not a reactant because it's clearly increasing, which makes it a product. But you can just use the graph to define these different things. So if you look at the beginning and then you draw a line tangent to that beginning of the curve and then determine the slope of that curve, that equals what's called your initial rate of reaction. All right. Now, you're not going to have to do that yourself. That data will be given to you in a tabular form. All right. And what happens is they start with different amounts of reactants and then measure what that initial rate is in those different experiments. All right. There are a couple other types of rates that you can look at. I just wanted to find them quickly. All right. The first is, or the second rather, is going to be an average rate. So let's say we wanted to know the average rate from this time point to this time point. All right. Well, we would just draw a line between those two. That's a terrible line. This, and then the slope here would equal the average rate over this time period. All right. And then the last one, it's called an instantaneous rate. I'm going to change my color just so you can see it. So let's say we want to know, well, what is the instantaneous rate at this particular time point? Well, for this one, it's going to be a tangent. Let's see if I can draw this. Oops, that's not it. And you're going to draw it so it's tangent to the curve right at that point. All right. And then the slope here is going to be equal to the instantaneous rate at set time point. All right. As I said, though, for our purposes, when we deal with differential rate laws, we're most concerned with this initial rate. All right. I just wanted you to know what those other rates meant because they do pop up in questions sometimes. All right. So, as I said, the power must be determined experimentally using that that initial rate data. All right. The sum of the powers for all reactants is called the rate order of the reaction. Now, if you look at each power individually, that is the rate order for that particular component. But when you add those powers up, you get the overall rate order of the reaction. All right. And that is useful information because it's going to help us with units for K, which maybe I should tell you what K is. All right, there's also in these rate laws included what's called a proportionality constant, which is represented by a lowercase k. All right, this is temperature dependent. So if you change temperatures, the K value will change. So you'll need to recalculate it at a different temperature. All right. And its units can tell you the overall reaction order. And we'll talk about that a little bit at the end. All right. Generally speaking, the larger K is, the greater the reaction rate, and vice versa. Now, there is a formula for K that is separate from initial rate data or differential rate laws, which includes things like number of collisions, orientation, energy, which really gets at how the collisions of these particles inform this K value. But again, that's going to be a little bit outside the scope for AP Chem if you take Gen Chem, and then particularly if you take organic and biochem, where you'll deal with kinetics, you're going to learn whole lot more about that. But I don't want you to think of this proportionality constant as some random number. It really does feed back into how many collisions are we having, how many are in the proper orientation, how many have the correct energy. So, in other words, what proportion of all of our collisions are leading to successful reactions? That's really what K is. All right. So, what does a rate law look like? If we're talking about differential rate laws, we're going to do a problem down here below, but generally speaking, the rate is equal to K times the concentration of your reactants raised to some power. Well, maybe I should make this an A. All right. The concentration of A and X are what we're going to be, not the concentration, sorry, let me back up. The X is what we need to determine using experimental data. This could also be A raised to a power B raised to a power C raised to a power. It just depends on how many reactants you have in a particular chemical reaction. All right. Now, how do we calculate that X value? Well, we need this initial rate data, all right, which we have a table of it right here. All right. And to calculate what that exponent is, you're going to take the rate for one experiment and set it in ratio to the rate of a second experiment. And you're going to set that equal to the concentration of your reactant in the first experiment divided by the concentration of your reactant in the second experiment. And those two sides, those two ratios, are equal to each other through the presence of this power X. All right. So we're going to solve for X. We'll know the other four numbers, and X is going to be our unknown. All right. Now, one thing to keep in mind is when we have a reaction like this one, we've got CH3CBr plus water forms CH3COH plus HBr. All right. You want to limit the number of variables that are present. So that means that when I want to look for the order, which is our power, with respect to a specific reactant, I need to choose experiments where the other reactant concentration, the other reactants concentration, oops, is constant. All right. In other words, I want the only factor impacting the change in the rate to be the change in the concentration of my target reactant. I want to make sure the other reactant is not changing. Therefore, it is not also impacting the rate. All right. So if I look at these experiments, I want to keep the amount of H2O constant. All right, so I can see that they're constant for experiments 2 and 3. So I'm going to look at the data for experiments 2 and 3 and use that to set up my ratio to solve for X. All right, so in other words, I'm going to focus on experiments 2 and 3. All right, so I always put the larger number on top and the smaller number on the bottom. All right, so the rate for experiment 3 is 4 times 10 to the negative 6 divided by 2 times 10 to the negative 6th. All right, on this side, I use the concentration values that match those rates. So for experiment 3, for my CH3C CBR component is 0.1 for the initial concentration for experiment 3 and 0.05 for the initial concentration for experiment 2. And then that will be raised to a power. All right, so I do the division on the left side and I get 2. I do the division on the right side and I get 2. So 2 raised to some power equals 2. All right, well, 2 raised to the first power will give me the same number back. So that means that x must be 1. All right, so first order for CH3 3CBR. That's what that tells us. Okay. All right, now we're going to repeat that setup, but this time we're going to be looking at water. So we need to choose 2 experiments where water is constant. Where CH33CBR is constant. So we're going to be using experiments 1 and 2. So that means we'll be using these 2 rates this time. All right, so the same idea, except this time we're going to focus on experiments 1 and 2. All right, the larger number first. All right, well, if we look, we've got a rate of 2 times 10 to the negative 6 for experiment 2 and 2 times 10 to the negative 6 for experiment 1. And then for our concentrations, 0.040 for the concentration for 2, 0.020 for the concentration for experiment 1 raised to some power. All right, so we end up with 1 equal to 2 raised to a power. All right, so the only power that I can raise to 2 and get 1 back is going to be 0. All right, so this is 0 order for H2O. Now that means that the concentration of water has no effect on the rate of the reaction. All right. So when we write the overall order, we need to add these 2 values together. That will give me my overall order. So 1 plus 0 means the overall reaction order is first order. All right. To write the rate equation, I think the other way to say this is to write the rate law. That's probably better. The rate of the reaction is equal to K times the concentration of CH3 3CBr. And now you don't have to put the 1 there. It's understood if there's nothing there. Times the concentration of H2O raised to the 0 power. Now I wrote it in here, but generally speaking, when you have something raised to the 0 power, you erase it. You do not include it. All right. So that shows you that the rate here is only related to the concentration of that first reactant. All right. Now, the last step to most of these problems is then to calculate K for this reaction. So to do that, you choose any of the 3 experiments you want. All right, I'm going to go with experiment 1. And then you plug in the rate and the concentration for that experiment and solve for K. All right, so 2.0 times 10 to the negative 6 molar per second equals our K value times 0.05 molar raised to the first power. All right, so we're going to divide 0.05 to the other side, and we find that K is equal to 4.0 times 10 to the negative 5th. And my unit here, the molar is going to cancel. Oh, wait, did I mess my rate up? Yes, this rate should be molar per minute. So I'm going to be left with 4.0 times 10 to the negative 5th per minute as my value for K. All right, now I could be given initial amounts of my reactants, and now that I know K, calculate what the rate would be for those amounts of reactants. All right, so once you determine K for a particular reaction at a particular temperature, it's good for any initial amounts of reactants that you may have. All right, so now we're going to move on to this second question. All right, it's similar. All right, we've got a reaction, 2MnO minus, sorry, 2MnO4 minus plus 5 oxalic acids plus 6 protons yields 2 manganese ions plus 10 carbon dioxides plus 8 waters. Okay, so we're using the initial rate data to find the reaction order for each reactant. All right, so I'm going to start with MnO4. So I need to pick two reactions where the other two reactants are held constant. And if I look, it's going to be experiments 1 and 2. I'm just going to number these. 1. All right. So for MnO4 minus, I'm going to use experiments 1 and 2. All right. So I do exactly what I did before. All right. 8.0 times 10 to the negative fourth divided by 2.0 times 10 to the negative fourth is going to be equal to 2.0 times 10 to the negative third divided by 1.0 times 10 to the negative third raised to the power x. All right, so I'm going to get 4 on this side equals 2 raised to the power of x. So what power can 2 be raised to get 4? Well, that's 2. So we are second order in reference to the MnO4 minus. All right, now I'm going to repeat H2C2O4, oxalic acid. All right, I go back and I look. All right, so I need to hold the other two constant. So that's going to be experiments 2 and 3. And then I'm going to set up just like I did before. All right, so 1.6 times 10 to the negative third divided by 8.0 times 10 to the negative fourth equals, and then on this side, 2.0 times 10 to the negative third divided by 1.0 times 10 to the negative third raised to some power. I'll make it y this time. All right, so I do my divisions. I have 2 equals 2 raised to the y. So in this case, y is going to be equal to 1. So it's first order in reference to oxalic acid. All right, then I end by looking at H plus. All right, so I need to find 2 experiments where everything is the same, and that looks like that's going to be experiments 3 and 4. All right, and I set everything up just like I did for my other 2 reactants. 1.6 times 10 to the negative third divided by 1.6 times 10 to the negative third. Oh, the rate didn't change. Well, you know what that means. So 2.0 divided by 1.0 raised to the power z. So I get a 1 here, 2 raised to the power z. So the rate was not impacted by the change in the amount of H plus. So that tells me that it is 0 order in reference to the H2O. All right, so I now know the powers for each of my reactants, and I can write my overall rate law. So the rate is going to be equal to our proportionality constant times the concentration of MnO4 minus squared times the concentration of H2C2O4 raised to the first power. And I exclude H2O from my rate law because it is to the 0 power. All right, now I want to calculate K. All right, so I'll just use experiment 1's data. All right, so for experiment 1, the rate was 2.0 times 10 to the negative fourth. Let me make sure I get my units right this time. Molar per second. So that's going to be equal to K times 1.0 times 10 to the negative third molar squared times 1.0 times 10 to the negative third molar. All right, so when I do my units here, right? Well, let me just do it out. I'll do it on. We'll keep everything the same. So this is 2.0 times 10 to the negative fourth molar per second equals K times 1 to the negative third squared times 1 to the negative third. So I'm going to get 1 times 10 to the negative ninth, and the unit here will be molar cubed, right? Because I squared it and then I multiplied another molar in there. So when I divide that over, that'll cancel that molar that is up on top of my rate unit, but leave 2 behind. So in other words, K is going to be equal to, let's see, 1, 2, and then negative 4. 2.0 times 10 to the fifth. And the unit here will be per molar squared seconds. All right. The units for K are very important. So you need to make sure that you list them with your K value. So make sure you are paying attention to what those are going to be. All right. Now, the next question, by what factor, whoops, would the initial rate change if the concentration of all three reactants were doubled? All right, so what I've got here is a question about how the overall rate order is going to impact the rate when we have changes. All right, so if we think about it, we've got a rate, it's going to be equal to some constant. All right, let's say that we went from 1 squared and 1. So this is what it looked like. So this would give us a rate of 1. All right, now let's double everything. So rate is equal to K times 2 squared times 2. All right, so 2 squared is 4 times 2. So this is going to be a rate value of 8. So you can see that the rate will increase by a factor of 8, which makes sense. The reaction order overall is 3. All right, so that means that whatever we do to our concentrations, we need to cube it in terms of what it's going to look like for the rate. All right. If our overall reaction order was 2, then we would square it. If the overall reaction order was 4, we would raise it to the power of 4. All right. Now, determine the rate of the reaction when MnO4 minus has a concentration of 0.5 molar and the oxalic acid concentration is 0.75 molar and the concentration of H plus is 2.5 molar. All right, so this time we're going to use our rate law and our known value of K to figure out what the rate is under these initial concentrations. All right, so there's K. And then I'm going to take my concentration of MnO4 minus, square it. And then I'm going to take my concentration of oxalic acid, raised to the first power. And then I'm going to exclude the water, the H plus, because it was a 0 order. So it doesn't matter. All right. When I plug all of this in, all right, I'm going to get 37.5. Now my units, if you look, this is going to give us molar cubed, right? And when I multiply molar cubed by this unit right here, 2 of those molar will cancel and we're left with molar per second, which is the unit of a rate. All right. Now, I want to take a moment. This is not on the worksheet, but I want to add this in. All right, to talk a little bit more about what the reaction order means and then what that means in terms of the unit for K. All right, so what does the reaction order mean? Whoops. All right, so let's start with 0 order. All right, so let's say that we look at the initial rate data and we find that the rate is equal to K times the concentration of our reactant raised to the 0 power. All right, so what that really means is that rate is just equal to K, right? Because anything raised to the 0 power is 1, and 1 times K is K. All right, so if you do adjust the concentration of A, let's say we increase it by a factor of 2, the rate remains the same. All right, because according to the differential rate law, there's no impact on the rate by that concentration of A. All right, now let's look at first order. All right, here, the rate would be equal to K times the concentration of a reactant raised to the first power. All right, so in this case, if the concentration of A increases to X, then the rate also increases by a factor of 2. All right. You can think of it as whatever happens to A is going to happen to rate because it's raised to the power of 1. All right. And then let's look last at second order. All right. So we have two options here, really. Rate is equal to K, one reactant raised to the power of 2, or we could see a rate law where we have two reactants, but both are to the first power, which would still give us an overall rate order of 2. All right, in either case, all right, if we'll look at that first one, if the concentration of A is increased to X, then rate will increase 4X. All right, if concentration of A and concentration of B are increased to X, then rate will increase again by 4 times. Okay, so that's really what's happening. That's what those rate orders are doing for us. They are impacting the rate when we change the concentration of our reactants. All right, now the other piece that's really handy is the units or K, all right? If you're given a rate law constant with its units, you can use those units to determine what the overall reaction order is for that particular reaction, even if you do not have any initial rate data. All right, so again, let's start with zero order. All right, again, rate is equal to K times the concentration of A, whoops, raised to the 0 power, or that rate really just equals K. So that means the units of K have to match the units for that rate. All right, so a rate is in molar per second, which means that K's unit is going to also be molar per second or per minute, whatever that rate is being given in. All right, now let's look at first order. All right, again, here the rate is equal to K times the concentration of the reactant raised to the first power. All right, so if we think about it, this is molar per second is equal to K times molar. So when we divide this over, all right, the molar is going to cancel. All right, so K is going to have a unit of per seconds here. All right, so you can see we went from molar per second to just per second as we increased our rate order by 1. All right, I want you to keep an eye on that pattern. Second order. I'm just going to keep it with A just to keep it simple. All right, but you could have A times B. But the rate equals K times the concentration of A squared will give us a second order. All right, so again, meters per second equals K times meters squared. All right, so when we divide this over here, all right, then the molar part, not meters, molar portion of the rate unit is going to cancel, but we still have one left. All right, so that unit for K is going to be equal to per molar times seconds. All right, so we went from molar per second to per seconds, now per molar seconds. All right, so you can see the molar goes away and then starts to pop up in the denominator. All right, I want to do one more just so you can see it. Third order. All right, now an example of a third order would be rate equals K times A raised to the 3. All right, that would be an example of something. All right, so again, we're going to have molar per second for our rate unit, and then K times molar cubed. All right, so again, we'll divide that unit over. The molarity on the top of the rate will cancel, but we're left with 2 molars now. So 1 over molar squared per second. All right, so you can see that the molar portion is increasing in the denominator as we increase. All right, and just for funsies, let's say we have something that is sixth order, and I wanted to guess what that would be, the unit for K would be. I would say it's going to be 1 over molar raised to the 5th power times seconds. So see how this unit is always 1 less than the order. All right. If you were given a K value of 1 over molar to the third times seconds, all right, I would use that to determine that it was a fourth order reaction. Okay. So the units for K can be very handy when determining the overall reaction order. Okay. All right. So again, differential rate laws are going to be different than our relative rate laws in that they focus only on the reactants. All right. They are expressed as rate equals the proportionality constant K times the concentration of our reactants raised to some particular power. Right? That power must be determined experimentally using initial rate data. And when you want to determine a particular reactant's power, you need to choose experiments where the other reactants are held constant. Okay. The sum of all those powers together is going to give you the overall rate order for that reaction, which in turn informs the unit for K.